Welcome to Lesson 4B. The advances in cancer research have not eliminated the disease, but they have increased the probability of a longer life. This lesson helps you to be more critical about data when they are presented to you. How do you think the mortality rate on the cancer website was calculated? Hit pause, add an answer or two, and then come back. So one answer you might have said about the mortality rate on the cancer website is that you could divide the people who died by cancer of the total number of people who have cancer. You could divide the number of people who died from cancer by the total number of people who died. We're going to be looking at probability of an event occurring given that another event has already occurred. We're going to be talking about what's the probability of dying from cancer given that you already have cancer. Again, I know this can be a very sensitive topic, and I'm aware of that. We're talking about the numbers without disrespect for people who have had or have died from cancer. Our objectives for this lesson are that we'll understand the concept of, oh wow, that was a big pen. That we'll understand the concept of conditional probability, including dependent events. We spent all of 4A talking about independent events. Now we've got to change gears and focus on dependent events. Another item that we'll understand is how conditional probability can help us to understand the risk of different situations. And finally, we're going to calculate conditional probabilities for two or more dependent events. On your glossary that you've started or flashcards or however you're keeping up with vocabulary words, here are some that you need to add. Dependent events. Events are considered to be dependent if the outcome of one event affects, impacts, makes a difference in the outcome of another event. Conditional probability is the measure. It measures the probability of an event given that another event has occurred. It's conditional. It's based on some conditions. If the events are A and B, respectively, then what we say is the probability of A happening given that B has already occurred. It is commonly denoted by the probability of B with this long bar, B, and we'll be pronouncing it, what's going to be the probability that A is going to happen given that B has already occurred. Like, what's going to be the probability of dying from cancer given that the individual already has cancer. We're going to explain the conditional probability of dependent and events a little bit better, differently, but I still remind you, you can start and stop the video anytime you want to process information, or again, you can just keep listening and maybe it'll gel as you go through, but don't leave this lesson until the ideas do fully make sense. This is talking about conditional probability of two events, and they're dependent, the conditional probability of A and B happening with dependent events is calculated when multiplying. So in other words, keeping in mind what we did with independent events in 4A to have that straight in your brain and how it's similar to what we're about to do, but yet how it's distinguishably different. So the probability of A by the probability of B, we're going to be multiplying these. In other words, what's going to be the probability of A and B occurring? In other words, somebody having cancer and dying from cancer. But we're going to talk about drawing balls out of a bag first. So what's the probability of A times the probability, and I said this all backwards, probability of somebody dying from cancer given that they already have cancer. Let me stick with the balls first, and then we're going to rewrite some of this. So if we have a bag that has 4 yellow, so let's go ahead and get 4 yellow balls and 6 blue balls. And these are all in this handy dandy bag with a little tie on the top, looks like a balloon. And what they're asking us, what's the probability of drawing a yellow ball first and a yellow ball second? In other words, what's going to be the probability of drawing a yellow ball and a yellow ball? It's going to be calculated by multiplying the probability that the first ball has been drawn in the first place, and I'm trying to rush. I need to slow down and just say this. We've got a lot of stuff going on here. We're going to be talking about this, as it says at the top, dependent and. We're going to have formulas. We're going to look at different formulas, but first, let's look at a visual. We have a tree diagram. We have me drawing a balloon-looking thing with a smiley face dots in it. But what this whole diagram is trying to explain to us is that if there is an event of what's the probability of drawing a yellow ball and then drawing another yellow ball, they're explaining it using the tree diagram with the events here and the events here. Up here it said the probability of drawing yellow and yellow is going to be the probability that you draw yellow the first time, and then the probability the next time that you are going to draw another yellow, given that you drew a yellow the first time. This is so much easier than what I'm saying. So if we go over here to our bag of marbles, bag of whatever, and we go over here to this bag, and we reach our hand in the bag without looking, what is the probability that we're going to draw a yellow ball the first time? And so the formula is saying that. What's the probability of drawing a yellow ball? And then we're going to multiply it times the probability that we did, and then we get another one. Let's start with the probability of a yellow ball. In this bag, there are 4 yellow balls out of 10 total balls. So the probability of drawing a yellow the first time you stick your hand in there, 4 out of 10. We can reduce it to 2 out of 5. I'm going to hang right here for just a second. But then the second part is, what's the probability of drawing a yellow given that you drew a yellow on the first try? And this is where you really need to hone in on this second row of results. Because on the first row, here's what we got going on. We drew 4 out of 10. That's what we've got going on right here, 4 out of 10. That we will stick our hand in that bag and grab yellow, 4 out of 10. But then the next question is, we stick our hand back in the bag, and there are not 4 yellow balls in there anymore. This is now dependent on the event that just occurred. We don't have 10 marbles, 10 cotton balls, 10 whatever in there anymore. We only have 9, and in fact, only 3 of them are yellow because this is dependent on that we drew a yellow the first time. So I'll scroll back up to the top of the page, and all this is trying to illustrate is that there's going to be a formula. And the formula is going to say, what's going to be the probability of this and this? And boy, that was a horrible, whatever that thing was I just drew. What's going to be the probability of both events occurring, and they are related to each other. They are dependent on each other. Or we're going to take the probability that the first one happened, and then the probability that since the first one happened, what's going to be the probability that it could happen again, or whatever it is, because they depend on each other. So very simply, with our bag of marbles here, if we reach our hand in there the first time, 4 out of 10 is the probability that we will get a yellow ball. But then once we do grab the yellow ball, then we've got 9 in the bag, and only 3 of those are yellow. When we multiply these together, either top times top to get 12 over 90, and then we can start reducing out parts like 3 times 4 and 3 times 30. Well, that got a little bit. Let's do this again. 2 times 2 and 2 times 15. Well, the probability will be 2 out of 15. And if you look up here and follow the tree diagram, let me grab one more color. Let me grab yellow. Notice we had the 4 out of 10 that we would get a yellow, 3 out of 9 that we would get the next yellow. With all of the mathematics, woohoo, we match. But one huge note to put with all of your vocabulary, the final probability of all of the outcomes is going to add up to, well, you can't see it, but behind there is a 1, a 1. a 1.00, or as we can say, 100% of the events will all add up. Well, it'll all have to be 100% of the possible events. I like these lessons because they're scaffolded. They're leading us somewhere. They're helping us to grow in our understanding of the concept. So I'm about to do question 2, part A and part B. This is a great time to hit pause. You mess around with what's going on part A and on part B, and then come back. Looking at part A, it gives us a statement. I agree with that statement. If I have 3 times 4, it does equal 12. But then it does a rewrite. Oh, so what would be 12 divided by 3? Well, let me play around with this. If I did have 12 divided by 3, and I've run out of space, then that would mean to balance the equations, I have to do this over here, divide by 3. So what it means is 4 would be 12 over 3. That makes sense. 12 divided by 3 is 4. So then they take this very tactile number and then throw us into abstract very quickly. That's okay, because it's still like 3 times 4 equals 12. And then it just says what it said a while ago. Instead of 12 divided by 3, it says, well, what's z divided by x? So again, if I have x times y and it equals z, and they're asking us, what is z divided by x? Well, let me grab another color. What would z divided by x be? Well, I'd have to make sure I did the same process on the left-hand side, so it would be y. Y is worth z divided by x, just like over here, 4 is worth 12 over 3. So make sure part A makes a lot of sense, because now this comes to the concept that they're really wanting us to see. They've got this long equation, but it's just like what we had on part A. It looks like 3 times 4 equals 12. It was no biggie a while ago when we said, well, 12 divided by 3, oh, that'd be just 4. It's all okay. So the question is, so what is the probability of A and B? It's that part we're looking at right here. If it was divided by this front end, well, hey, that's what they did a while ago. They just divided this by 3. So let's just look at it. If we did have the probability of A times the probability of B, given that A has already occurred, and it equals the probability of A and B, well, this is saying, what if we had the probability of A and it was divided by probability of A and B divided by probability of A? So what if we had this? Well, that would mean we need to do it over here, just like we did on part A. These are 1, and we end up with a brand new formula that says the probability of B occurring, given that A has already occurred, here's the formula. You and I are going to go find what's the probability of A and B, sorry about that, and we're going to divide it by the probability of just A. You may want to go ahead and pause the recording right now, go ahead and read through this information, and then come back and we'll digest it together. It starts by saying, let's examine the American Cancer Society data again from the same website. Again, I'm reminding you, make sure when you cut and paste this into a browser, you do not have that period there at the end of the sentence. The article represents the risk for United States men. So we're going to have to start digesting. This is United States men developing cancer of all invasive sites. And then it gives us a percentage, a possibility, the outcome, the risk of this happening. And the risk of U.S. men dying from cancer as this. And I want to point out, I'm going to change colors, different color. This is the risk of men developing cancer, right here. And this is the risk of men dying from cancer. And it's all invasive sites, and we'll break it up into to certain cancers. But right now, this is all. Let's take a closer look at these statistics. These numbers are based on incident and mortality rates, and then they give us the years. The incidence data for getting cancer were determined by dividing the number of United States males who have cancer by the total males in the population. The incidence getting cancer. Mortality or dying from cancer was calculated by dividing the number of male deaths due to cancer in 1 year by the total number of male deaths during that time period. Let's look at it another way. Given all the male deaths in 1 year, what percent were due to cancer? The mortality rate, though, does not tell us what the chances are if you are male and diagnosed with cancer, or what your risk is for dying from that cancer. In other words, the two sections of the table have different base numbers. So let's translate all of this into our probability notation. For right now, go ahead and do questions 3, 4, and 5, and hit pause, do those questions, and then come back. Using the information that we just read, question 3 asks, what's the probability that a U.S. male will have cancer in his lifetime? And then it says in our directions, round to the nearest percent. Oops, sorry, I'm looking at the wrong one. The risk that men will develop cancer is 43 and 92/100%, but the nearest percent is going to put us at, I'm so sorry, I'm looking at the wrong numbers. In the article, 42 and 5/100% is the risk for United States men developing cancer at all invasive sites. But the directions ask for nearest percent, and so when I look at the tenths place, that tells, y'all, I'm so sorry. That's going to get me at 42%. Wow, that took a while. So what is the probability that a United States male will die from cancer? So in the article, it says 22 and 62/100% to the nearest percent. My 2, looking at the 6, is going to go to 23%. But I want to note that this is representing the probability that someone will have cancer given that they're male. That was 42%. And this one's probability that someone's going to die from cancer and that they are given that they're male. And here's their percentage. Remember, you can start and stop this video as much as you need to slow this down. You might want to speed this up, but to slow this down to talk about these probabilities. Make them make sense. Use your own words, your own terminology, talk it out to yourself. Like, the probability that a male will die from cancer given that he has cancer. I'm going to choose to write it like this: that dying from cancer, having cancer. What's the probability someone's going to die from cancer given that they have cancer? And the formula a while ago said it's the probability of A and B. In other words, they had cancer and they died from cancer, divided by the probability that they have cancer. When we look back at the numbers that we were just looking at, they asked us to round them, but I'm going to go back to the originals. What's the probability that you're going to die from cancer given that you had cancer? The numbers were 22 and 62/100%. Followed by what's the probability of being male and having cancer? And that was 42 and 5/100%. When we divide these, and I'm going to go ahead and do that because I'm not going to trust my notes right now. I've got 22.62 divided by 42.05, and I am getting oh my goodness, sorry y'all, I'm trying to look. I need to get the calculator up here. I'm getting this. And it doesn't tell us whether to leave this to tenths or hundredths. I think we're still under the round to the nearest whole number. This is a decimal. We're going to percent. I'm sorry, I'm writing up the page. This is hideous. So it's 53.54%, and let's just go on up the page one more time. And so rounding to the nearest whole number is going to put us at 54% is the probability of a male who has cancer that they will die from the cancer. I'm sorry, someone who dies from, man, this is not funny. As it says right here, what's the probability of a male dying from cancer given that he already has cancer? Go ahead and hit pause. You need to attempt, try, really work hard on 6, 7, 8, and 9 before watching the video, and then come back and we'll walk through these together. From the website, you may consider printing some information about females now, just to have it in one place, or you can always go back and forth from the video back to the website to get the data. Starting at question 6, what is the probability that a United States female would die from breast cancer given that she's diagnosed with breast cancer? So what's the probability that a US female is going to die from breast cancer given that she has already been diagnosed with it? And the female was going to die from breast cancer given that the female already has breast cancer. The probability is that I'm female and I have breast cancer and I have died from breast cancer divided by the probability that I'm female and I have cancer. If you look in the article, you're going to see that the probability of having breast cancer and dying from breast cancer is 2.69. The probability of having breast cancer is 12.32. When I divide and multiply by 100 and round to the nearest whole number, I'm getting 22%. I'm going to keep going. Stop the video as often as you need. Number 7, what's the probability that a United States female probability that a female is going to die from lung cancer given that she's been diagnosed with lung cancer? So we need to go find the probability that this person had and died from lung cancer divided by the probability that they only have, and not only use only lightly, that they have the cancer. When I looked through the numbers, I found for a female who has died from lung cancer, the probability is 4.89. The probability of having lung cancer was 6 400ths, which when I divide and multiply by 10 and round to the nearest whole number, I got 81%. We'll do this one more time on number 8. It says, what's the probability that a U.S., they switched up on us, male is going to die from lung cancer if he is already diagnosed with it? So what's the probability that the male is going to die from lung cancer given that you already have lung cancer? It equals the probability of dying from lung cancer and the probability of having lung cancer. When I look at the chart for the numbers, dying from lung cancer, the probability is 6 3300ths. Having lung cancer is 7 1900ths. And when I divide and round to the nearest whole number, I get 88%. I'm going to keep going. Again, I encourage you to start and stop the video as often as you need to process, but looking at question 9, do males or females have a higher risk of dying from melanoma of the skin, knowing that they already have melanoma? Show your solution process and explain your results. So I'm going to go undo a lot of what I've already done, and this is going to take a while, maybe, because I need a little bit more space because they're asking me to calculate for males and females separately to talk about the risk of dying from melanoma cancer. Going back to the article, I'm looking for melanoma males and melanoma females. So I'm going to go to males right here. And it's the probability that they're going to die from melanoma cancer given that they already have it. So the probability that they died from melanoma cancer, given that they have melanoma, the numbers I'm finding are 43 hundredths and 2 and 62 hundredths, which when I divide, multiply by 100 and round to the nearest whole number. For males, the probability that they're going to die from lung cancer, excuse me, I'm looking at the wrong line, die from melanoma, given that they've already got melanoma, is 16%. They want us to compare that to the female probability. So the probability that you're going to die from melanoma, given that you had melanoma. So what's the probability of females who have melanoma and have died, divided by those who just have melanoma? I find that it's 21 hundredths of those who have died, 1 and 63 hundredths of those who have females who have melanoma. When I divide, multiply by 100 and round to the nearest whole number, I get 13%. So the answer is men have a higher rate of dying from melanoma, given that they already have melanoma. We've shown our process, and our results are men have a higher percentage of risk. Go ahead and write down some thoughts on question 10. I'm not going to flip over to a different screen. I want to stay right here because the question asks, write a statement comparing and contrasting the independent and dependent events for the probability of dying from melanoma. You can talk about males, you can talk about females. Here's an example. Right here, the probability of someone being male and getting melanoma cancer is less than 1%. It's like less than 0.5%. But if a male does get melanoma, then their chance of dying from it goes all the way up to 16%. You can talk about going this direction. You can talk about the same thing for females, that for a female, the probability of a female getting melanoma is way low. It's like just nowhere near 1%. But if they do get melanoma cancer, then they have a 13% chance of dying from it. Make your comments, and this finishes lesson 4B. You need to look at your calendar to see if you have any more lessons for this week to do before the deadline.